So hello everyone, this is lecture 3 for the classical physics, in which we were studying about the stability analysis, equilibrium points and all, and we were discussing some questions. So I have given you these two questions to you. So let's see the solution. So there was this consider motion of a classical particle of mass 1 unit in 1D double well potential well this. So first try to plot this graph. How you can plot? Put Vx equal to 0 and find the points. You will get plus minus root 2. So at plus minus root 2 it will be 0. Then try to find the equilibrium points. So differentiate it. You will get this. So at x equal to 0 and x plus minus root 2 you will have the equilibrium points. Now find the minima and maxima by second order differentiation of this. Then find the values at 0 and plus minus root 2, plus and minus you will get. So you will see that at 0 this second order derivative will be less than 0, so you will get the maxima, and for these you will have the minima. So this plot will be look like this. Okay, so you have these two potential wells, so where particle can oscillate. It is right well, it is left well. Now you need to find the frequency of the particle if it will oscillate in this region, in this well. So how you can find the frequency? You know the formula, del square v by del x square at x equal to x naught divided by m. So m is 1 unit, and if you see this second order derivative will be this 3x square minus 2. So at root 2, what will be the value of this? 2 is 6, 6 to 4, 6 minus 2 4. So value of this is 4. Substitute it here. So under root 4 will give you 2. So frequency will be 2. So we'll see in this question. So B option will be right. The particle will execute SHM in right well with angular frequency 2. Okay. So particle will switch between right and left. So it can't possible because there is this potential barrier. Potential barrier. That's why it can't switch from these two wells. In the last stage, particle will approach bottom of the well and settle. So in the question it was given that friction is neglected. That's why if particle is given some energy, then it will always oscillate in this region. It will never get back to the base. Okay, that's why D is incorrect, C is incorrect, and A is incorrect. Only B is right. Now this was also the question. Particle of unit mass is given speed 1 meter per second at unstable equilibrium point of potential this. What will be the speed at a stable equilibrium point? So if this kind of question can be asked, so just it has a simple solution. Just put the total energy equal the conservation of energy. Use that thing. Means at the unstable point, find the potential energy and the kinetic energy, and at unstable point, find the potential and kinetic energy. Then you can find the velocity. How? Potential is given by this formula. So first find the equilibrium points. So del E upon del x, it will give you these 2 points as equilibrium points. So first find the potential at 1 by root 3 and 1 minus 1 upon root 3. So you have these potential energy at stable and unstable equilibrium points. Okay. Now at unstable equilibrium point, you know the potential kinetic energy because speed was 1 meter per second. So half mv square will give you the kinetic energy at unstable equilibrium point. And from here you can get this. Means at minus 1 upon root 3 you will have the unstable equilibrium point. Okay, so you have the potential energy and you have the kinetic energy. The sum of these two, half mv square plus 2 upon 3 root 3 will be equal to the total energy at the stable equilibrium point. That is half m is 1 unit, it is v square speed at the stable equilibrium point, and it is potential energy at the stable equilibrium point. So just solve this equation, find the value of v, you will get this as your answer. Okay, just remember these tricks and these laws. So in today's lecture we will study about the phase trajectories. This is a very interesting topic, and many kind of questions can be asked from here. So pay attention. So we will discuss questions and then we will write some definitions. Okay, this is a good way to teach. Okay, so let's see. Draw the phase trajectories for 1D harmonic oscillator. So let's draw. So first let me define for you what is phase trajectory. Here we plot the trajectory in terms of we have the axis of momentum and the position. Okay, that kind of plot is called the phase trajectories. Okay, So let's try to plot for the 1D harmonic oscillator. For this, we have potential energy as kx square by 2. We know for the 1D harmonic oscillator, potential energy is this kx square by 2. And if we plot the energy curve, potential energy curve, so this is parabolic. So you will get this kind of curve. This is not phase trajectory. This is just a energy curve. We already discussed about this. So this is energy curve. Now first write this equation. Total energy equal to E, P square by 2, and represent the kinetic energy. Vx is potential energy, and this. So Vx is nothing but this. So this is a kind of graph. So if we plot P and X, then we can see here that it will give us a elliptical structure something. Okay. If we plot P and X on the Y and X axis, then we will get elliptical structure because it is a equation of ellipse. So how we can plot this? Let's try to plot if it will be a ellipse or not. Let's see. Now just I redrawn this graph here. Okay, so we will have three cases. First, let's say the particle have energy less than 0. So particle is somewhere here. So if particle has less than 0 energy, then it will be a classically forbidden region, because all the potential energy is greater than total energy. That's why this energy is of no use, and particle will won't be doing anything. Next is E2, that is particle can exist at x equal to 0 and it will be remain at rest. Means now energy is E2, so only this region is possible, and particle should be at rest at this point, at rest this point. Okay, this will be the second condition when E2 equal to 0, when the energy is E2, that is 0. So this will be the condition. Now there is third condition, the main about which we will discuss. When energy is greater than 0, then it will came somewhere here. We take E3 here. So we will have a potential means classically allowed region in which the particle can oscillate. So we will have the phase trajectory. So let's see what kind of phase trajectory we will have. So let's say we given this energy when the particle is at the origin. Okay, then it will start moving in this side, right side. So if it is moving here, you can see if the particle is moving this side, then potential energy is increasing, and when potential energy is increasing, kinetic energy will decrease, and kinetic energy will decrease, then we will say kinetic energy directly related to the momentum. So momentum will also decrease along this direction. So at origin it will have the maximum, because at this point potential is 0. So from this equation, at x equal to 0, P will be root 2me. So let's plot the P and X graph. At 0 we will have root 2me. Here will be the point. Now as we go to the right, then we will see that potential energy increasing and kinetic energy decreasing. So momentum is also decreasing in this direction. So we'll draw it like this. And when it reaches here total energy equal to potential energy, and kinetic energy will be 0. And when kinetic energy is 0, so our momentum will be 0. So that's why we drawn this curve like this. Okay, now because of the restoring force in the harmonic oscillator, particle will go back, and when it will go back, then this direction is negative x-axis. So when the negative x-axis, then it will be velocity will be negative and momentum will be negative. So whatever curve will be there, it will go like this to the downside because of the negative momentum. Now potential energy is decreasing, then kinetic energy will increase and momentum will increase. Okay, in the negative direction. So it is increasing in the negative direction. Now at this point, when it is moving in this direction, here it will have the maximum kinetic energy. Okay, and potential will be 0. So it will be minus root 2me because it is in negative direction. Then it will go again the same. Potential energy will increase, kinetic energy will decrease. It will be at 0 here, and that's how we see that it is 0 here. Then again because of the restoring force, it will go like this, and again potential kinetic energy will increase, so it will go like this. So this will be the curve we will get. So from here we know it is ellipse, that's why we drawn this as ellipse. Okay, now this is the condition we discussed. So for all the energies above 0, we will have this kind of curve. If we decrease some energy, it will be here. If the energy was here, then we'll get just this curve. and if energy is little bit greater, then we'll have this kind of curve. Okay, now you can find these points as when p equal to 0, substitute here, you will get x equal to root 2e by k. So here it is root 2e by k. When x equal to 0, then you will get p equal to root 2me. So that's why this condition. Now what is the area of this curve? You know it is ellipse, so area of ellipse is pi ab, where a is this, b is this. So it is this distance is this, distance is this. Let's multiply. Try to find the area enclosed by this face curve. So it will be this. So we'll get this. Now it is 2 pi root m upon k. So root k upon m is omega. So it will be 2 pi upon omega, and 2 pi over omega is t, the time period. So area enclosed represent actually the product of time period and the total energy. Okay. So remember this. So this is conclusion. In case of 1D harmonic oscillator, phase trajectory is elliptical. So this plot is called the phase trajectory. Now let's see something interesting, more interesting. Draw the phase trajectory for a particle moving in 1D potential, and potential is given, so we need to draw the phase trajectory. So how can we draw? Let's see. So potential is this minus 1 upon 2 kx square. So this minus sign represents that it will be a parabola because of x square, but it will be in the negative direction of x-axis. So this kind of parabola we will get for normal energy curve. This is not phase trajectory, this is energy curve. So we'll get this kind of curve for the potential. Now if we write the total energy equation, it will be kinetic energy plus potential energy is this equal to total energy. So when you see this equation, you can remember that this is the equation of a hyperbola. Okay, so hyperbolic curve you will get. So this will be hyperbolic. Now we will see how it came to become this. Okay, so this is the interesting thing. So first let's discuss if energy is less than 0. Okay, if energy is less than 0, then what will happen? In this region from here to here, we will see that total energy is less than potential energy. So this region will be classically forbidden. Particle can exist in this region, but not in this region. Okay, so let's say we have particle here, and we launch the particle from this side. Okay, this side, energy here. Okay, we launch the particle from this side, and as it is moving in this direction, we will see that potential is increasing, then kinetic energy will decreasing, and potential will be decreasing, sorry, momentum will be decreasing with the kinetic energy. And so the curve will be like this. When it is going in plus x direction, so momentum will be in this direction. So this momentum is decreasing when it is going like this because of increasing potential energy. And at this point, when it came like this here, then total energy will be equal to potential energy, and kinetic energy will turn out to be 0, and our momentum will be 0. So this graph will go like this up to here. Then we will see because of restoring force it will deflect. Then we will see that potential is decreasing and kinetic energy will start increasing, and in the negative direction. So momentum will be in the negative direction again. Okay, so now momentum will start increasing in the negative direction. So it will go like this. So this will be our curve. Same we can see in the right hand side. If particle, you launch the particle in this side, so momentum will be in negative direction, and as it is going this side, so potential is increasing and kinetic energy decreasing, so momentum is decreasing but in negative direction. So let's see, this will go like this. Momentum is in negative direction, so that's why we plotted it in downside, and it is going up to this point. At this point, total energy equal to potential energy, kinetic energy is 0, and momentum is 0. So it will go here. Then restoring force will reflect it back. Then kinetic energy will increase and potential energy will decrease. Okay, so momentum will increase in the positive direction. So it will go like this. So this type of curve we will get for this energy which is less than 0. Okay. it will be same for all the energies which is less than 0. This kind of curve we will get. Now let's see when energy is equal to 0, means on the x-axis. Now we will see particle should be here, it should be at rest. Okay, so if particle is coming from this side, then potential energy increasing, kinetic energy decreasing, and it is decreasing, then momentum is decreasing, and this will be a straight line. Why? Because energy is 0. Just substitute in this equation equal to 0 and try to plot p and x, you will get this kind of equation, this. So this is a linear equation, okay, equation of a line, and its slope is this. Okay, so we'll get, and we don't have any coordinate on the xy axis because of this. Actually, I mean we don't have any intercept, okay, because there was some constant, then it will give us intercept, so it will pass through the origin. Okay, at x equal to 0, p should be 0. So when energy is 0, the phase trajectory should be a straight line. So when it is going from here, momentum is decreasing and kinetic energy is also decreasing, so it will go like this. At origin, total kinetic energy is 0 and momentum is 0, so it will end here, the trajectory will end here. So these others are different cases. In this case only this is applicable, trajectory will end here. So when particle is going from this direction to this direction, then we will have negative momentum, and it is decreasing, and up to here it will decrease, totally decrease. So we'll get this kind of trajectory. This is for this one. And if particle is going in this direction, then kinetic energy increase, momentum increase, so we'll have this trajectory, start from this origin and go like this. If it is going from this to this, then kinetic energy increase, momentum increase in the negative direction, we'll have this trajectory. Okay, 1 2 3 4. So second case is clear to you, for the energy total equal to 0. Now let's have the third case when energy is greater than 0. Now it is somewhere here, energy. Now if you launch the particle from here, then again potential increase, kinetic energy decrease, and momentum decrease, but it won't be 0 here, because it still has some energy, and that energy will be its kinetic energy, which will make it go to this direction forever. Okay, and this is an example of unbound motion. There is no bound motion. Okay, so let's plot it. It is going from here to here, momentum is decreasing, so it will go like this, momentum is decreasing. At this point, what we have potential equal to 0. So when x equal to 0, potential equal to 0, substitute the value, and energy is E3. So x equal to 0 and here it is E3, so P will be root 2m E3. So at this point we will have momentum equal to root 2m E3. So if it is going like this, so at this point momentum will be root 2m E3, and if it has momentum, it will go on to this direction also. Now momentum is positive and it is increasing because potentially decreasing, so it will go like this after this. So this will be our phase trajectory for this condition when energy is greater than 0. Same if it will go from this direction to this direction, then we see that kinetic energy decreases and momentum decreases, and it will go like this, momentum is decreasing. It won't be 0, it will be minus 2 me3, because of the same condition, that at this point our potential is 0. So substitute here and we will get P equal to root 2 me, and it is because of this direction, it will be minus, momentum will be minus. Okay, and after this, if it is still having some momentum, it will go forever in this direction. So in this direction momentum is increasing because of decreasing potential energy. So this curve will go like this. Okay, so this will be our plot. So I hope it is clear to you, all the cases. So these are the cases, you can study them separately. So if you are still having any doubt, just put it in the comment section, I will try to resolve. Now try to solve these questions, then you will have more clarity about this topic. Otherwise I will solve in the next lecture. So write these questions. A particle moves in 1D under a potential Vx, that is alpha mod x, with some non-zero total energy. Draw the particle trajectories in phase space. Now second question is, draw the phase space trajectories on the pz plane of a ball bouncing perfectly elastically of a hard surface at z equal to 0. So in the A case, neglect the effect of friction. In B case, consider the effect of friction, that is non-elastic. Third question is, consider this graph. This is E1, E2. This is first circle. This is A. This is 2A radius. This is X. This is momentum Px. The phase space diagram for simple harmonic motion is a circle centered at the origin. This is phase space diagram. In the figure, two circles represent the same oscillator but different initial conditions. E1 and E2 are the total mechanical energy respectively. Then which option is correct? Means you have to find the relation between the energies E1 and E2. Okay, try to solve. We'll meet in the next lecture. Thank you everyone.